Okay, in this example, we are supposed to determine what the function f of x is, or how it's behaving on the intervals given. We're going to sketch the graph, or we can sketch the graph to assist. And then we're supposed to use increasing, decreasing, positive, or negative on each of the lines just to determine what it's going to be doing on, or to describe what it's doing on each of these intervals. Now, we can do this graphically. If you have a graphing device, you can easily do it with a graphing device. You can also do it graphically by sketching a rough graph, by figuring out each of the y values for each of the endpoints on the intervals, and then plotting the points and connecting the dots. However, based on this question, we can do it in a logical manner that takes advantage of the fact that there's some properties about polynomials that we have. So that's what I'm going to be doing here, is just taking advantage of the fact that it is indeed a polynomial and how the intervals are split up. You'll notice that the intervals here, one of them starts with -2 and ends with 1. So if I look at the other intervals, you'll see that this is the other set of intervals that has -2 and 1. So these two sets of intervals go together, which means if one of them is positive, then the other one's negative. If one of them is increasing, then the other one is decreasing. So what I'm going to do with that piece of information is I'm just going to write it down kind of below. And I'm going to write it in a way that you can kind of see the order of the intervals. So here are the two intervals that I'm going to focus on. That one, and do purple for the other one. These two are related. So the lower number would be the -infinity. So I'm just going to start by writing -infinity to -2. Then picking up with this interval, but I'm going to kind of stagger it down below just so I can see the difference here. -2 to 1 to make it easier to tell which interval is with which segment. And then from 1 to 3. And then from 3 to infinity. And that kind of covers the entire number line here. So we have the two intervals, and I'm going to shade over them just to emphasize which section is which. And then there's pink. Okay, I'm going to do the same thing with the other set of intervals. So I'm going to do the same thing with this set. So we have -infinity to -0.7. We have -0.7 to 2.1. And we have 2.1 to infinity. And I'll do again some shading just to emphasize which is which. Okay, that's that one. Okay, and there is the last one. Okay, now if we're not quite there in our unit with how my course goes, but I could also take advantage of the number of roots, the rational root theorem and stuff for polynomial functions. However, we're not quite there yet. So I'm just going to use what I've done so far, separating the intervals like this, and end behavior, which is one of the things that we have talked about in the course that I'm going through right now. So end behavior for this function, since it's an odd degree function, I know one side is going to go up and the other is going down. And because the leading coefficient is positive, I know that the right side is going to be going up and the left side is going to be going down. Which means I can figure out the intervals that deal with infinity, because one of the intervals will be going to positive infinity and one of them will be going to, or starting at -infinity. Now, if I'm talking about increasing, decreasing, well, as I go from left to right, both endpoints would be increasing from left to right based on this end behavior that I've kind of outlined. So I know that both infinities have to be increasing. Just if you look at my little arrows, I'm trying not to draw too many arrows here, but both the this arrow and this arrow, as you move from left to right, would be going up. Therefore, the intervals or the group of intervals that have both the negative and positive infinity in it would have to be the increasing intervals, which means this section of intervals here, because it has the negative and positive infinity in it, will be the increasing interval. Which also means, because these two are related, if one of them is increasing, the other one must be decreasing. With that being figured out, we know that the other ones must be positive and negative. Now, if this right end behavior goes up, that means eventually it has to be positive. In order to keep going and going and going upwards towards positive infinity, I know that at some point it has to be above the x-axis, which means the interval that contains the positive infinity will be a positive interval. I don't know exactly what's going on, but I do know that just by using some logic with the end behavior. So since positive infinity needs to be the positive interval, that means this is going to be our positive interval. With which by that nature, the other one is going to be negative. And that basically fills out all the information. But again, there are other ways to approach this. And as we go through the unit, we'll get more pieces of information that will allow us to kind of streamline this process and break down which interval, what it's doing on each of the intervals. And even find some of the intervals ourselves without it being given to us. In this example, we have a hot cup of tea that's left in a room that is approximately 40 degrees Fahrenheit. The temperature of the cup of tea is multiplied by the equation f of x, which is in degrees Fahrenheit, where x is time in minutes. What is the y-intercept, and what does it represent in this situation? Well, for the y-intercept is when x is 0. If you look at a graph, here's an example of y-intercept, and no matter what value on the y-axis you choose, we'll always have an x value of 0. So the easiest way to find the y-intercept is to replace x with 0. So if I go through and replace x with 0, plus 0.006 times 0 squared minus 1.05 times 0 plus 65.8. It's also nice with polynomials because whenever you're trying to find the y-intercept with a polynomial, if it's in standard form, then the y-intercept is also the term without the variable, or the constant term, because everything else will end up canceling out, leaving us with the y-intercept of 65.8. To describe what this represents in this situation, just think about the units. Well, the y value represents the temperature of the cup of tea, as quoted there. So this would say the temperature of the tea is 65.8 degrees Fahrenheit. And as far as what the variable x represents, because remember, any set of data points for a function requires an x and a y value. Well, the x represents time. And if you think about the x value for y-intercepts is 0, so what that would represent here is the temperature of the tea is 65.8 degrees after 0 minutes has passed. Which can be said in a number of ways, including when you first set out the tea, or at the starting temperature is 65.8 degrees Fahrenheit. So there's a number of ways to actually phrase this. But this is a general way, just looking at the units and just interpreting it for the situation.